Hello again. So last lecture, like two-part lecture, we talked about the birth of stars and what comes with the birth of stars, usually planets. There are those sort of pre-star stages, it's like clumps and cores and protostars. And it was once a star reached an interior temperature hot enough to start fusing protons, that's when we start calling it a star, right? And on the HR diagrams, that was when the object made it to the main sequence on that diagram. Now we're going to talk a bit about sort of the times after that. Adolescence to old age. They say adolescence here. Adolescence and adulthood, it's kind of all the same thing for a star. It's the time that it spends on the main sequence. Start out with a pretty picture. As per usual, this is what's known as a planetary nebula, and it's confusing because it doesn't really have anything to do with planets. It's a historical thing where a lot of them that we see look kind of round, and so when somebody was first spotting them, it seemed to look kind of like a planet to them, so they started calling it a planetary nebula. And we're just stuck with the name. Right? This is a late stage in a star's life, particularly a star like our sun will eventually make it to a stage like this. Make for some very pretty pictures. This is known as the Ant Nebula. Tough to keep track sometimes. You call a lot of things nebulas, different kinds of nebulas. So nebula, just like cloudish thing in space. We talked about your standard sort of nebulas, where these are stellar nurseries. Planetary nebulas. There was like a solar nebula we talked about a long time ago at the beginning of our solar system. But different kinds of clouds in space. So even though a lot of them are called nebula in one fashion or another, they're rather different sorts of things. Try to keep that in mind. Eventually we'll get to talking about this phase in a star's life, I think, in the second part of this lecture. Right, so a star has made it to the main sequence. Right? Fusion started. It is now what we officially call a star. And that takes a core temperature of about 10 million Kelvin. Once it's that hot, then the hydrogen will have lost all of its electrons a while ago, fully ionized hydrogen, and that's just a proton, the core of a hydrogen atom. And when it gets that hot, those protons start fusing together. And we have this proton-proton chain, which I told you about when we were talking about the inner workings of our sun. Our sun is just another star, and it's on the main sequence. It's doing the things that stars do when they're on the main sequence. Fusing hydrogen together to make heavy hydrogen, deuterium, and then fusing that with another proton to get helium-3, helium-3s together to get helium-4. So you're fusing hydrogen through this process to eventually get the stable helium out. So very slowly our sun is converting hydrogen to helium and letting out a lot of energy in the process. Hence, it shines very bright, and we wouldn't be here without it. If you recall, the end of the protostar was sort of collapsing in, and once fusion starts, then that generates a lot of energy in the interior and increases the pressure of all of the hydrogen that's in the interior, and so that pressure eventually is enough to balance out the force of gravity or the gravitational contraction. So gravity is still trying to crush everything in, but now we have a high enough pressure that's pushing out everywhere in order to balance that. And so we reach a state of equilibrium, meaning it's just balance between gravity and pressure, gas pressure. Again, we call that hydrostatic equilibrium. And we now say the star is on the main sequence. And this is most of the life of a star. It varies depending on the size of the star. We'll look at the timeline of that. But like our sun is like 4.5-ish billion years old. And it's going to be continuing to do this process to be on the main sequence for some 5 billion years or so more. And that's sort of its adulthood, right? Really just the longest period in a star's life cycle. So whether you call it adolescence, adulthood, I don't know. They're kind of the same thing. Yeah. So I'll probably be referencing it as adulthood. So during that part of a star's life cycle, it's very stable. It's not contracting anymore, right? The pressure is balancing out gravity. There's very little change in its mass. So hydrogen is converting to helium, and you're releasing energy. Some mass in the process is being converted to energy, but it's very, very tiny amounts. So overall, the mass of the stars stay roughly the same, and the cores of those stars are gradually changing. It takes a long time, billions of years usually, or for most stars, billions of years for that core to slowly convert from mostly hydrogen to mostly helium. So here's our good old HR diagram, and the main sequence then is that sort of diagonal, kind of waves a little bit, but starts up at the top left, down at the bottom right. So all the stars on that line are on the main sequence. They're all doing the same thing. They're burning protons, or fusing protons to form helium. And the main difference between all of them is the mass of the star. How much mass was around when it first started forming determines if it's way up here, really bright, really hot, not much mass around, way down here, cool and dim. Sun, sort of in the middle there. And just to remind you that the color in the background is just the rough connection to the temperature of these stars and their color, how they appear. So generally speaking, cooler, redder, hotter, they're more blue. Right. So how long are these stars on the main sequence? I think I've mentioned before, but generally speaking, the larger mass, or the more massive a star is, the quicker it goes through each of its steps in its life cycle. So the largest stars are the spectral type O, right, the left side of that HR diagram, the hottest temperatures, and that might be something like 40 times the mass of our sun. It only spends about 1 million years on the main sequence. Quite short a time in terms of cosmic timescales. Our sun, remember, is sort of like, is G class, G2. So this one that's G0, it's like slightly larger than our sun, 1.1 times the mass of our sun. It'll spend about 9 billion years on the main sequence. Our sun, mass 1 of our sun, is about 10. It spends about 10 billion years overall. You get to the really small end of stars, like 0.4 times the mass of the sun, or less than half the mass of our sun. This star is going to be on the main sequence for a long time, 200 billion years. And the overall idea here is that the really massive stars, like there's a ton of mass there, which basically means that there's a ton of gravitational energy, and gravity really contracts very hard for all of that mass. And so you end up heating up the interior of these really massive stars much hotter, and so they sort of burn through their fuel faster. And then on the other end, less massive stars, less gravitational sort of crushing overall, so the interiors are not quite as hot, and so they don't burn as quickly, last a lot longer. So even though the main sequence for that time is generally the longest time in a star's life, there's not a whole lot to talk about. It's sort of just burning away the hydrogen fuel, or the protons, fusing protons, and slowly converting its inner core to helium. It stays very stable. Billions of years. Well, our sun, billions of years. So not much more to say there, right? So we're ready to leave the main sequence. What does that mean? Well, that means that the hydrogen that was able to fuse in the core of the star has been exhausted. We've burned all that we can in order to fuse and make helium. And so the core ends up being more and more made out of helium, and helium requires a much higher temperature to fuse, and so it doesn't fuse, it's not hot enough inside the interior of the star yet, so it just kind of sits there and builds up in the core. And then eventually it builds up large enough where the hydrogen ends up kind of around it, just outside of it, to the point where that shell is far enough away from the actual core where the temperatures are high enough that it's not going to fuse anymore. Right? You kind of exhausted all the core hydrogen, and you still have this sort of hydrogen around that helium core. If the helium can't burn, the hydrogen is too far away to be hot enough to burn. You get to that area, that's about the point where this star is going to move off the main sequence again. So what happens? Once that helium fusion stops occurring in the core then, remember it was creating pressure in order to keep the star from contracting more. Right? So once you kind of run out of that helium, that pressure drops down, gravity can then start contracting the star again, or it kind of takes over. It wins over on the pressure now, and starts crushing the star again, right? And crushing the core quite a lot. And what that does is add a ton of energy to the helium that now makes up the core of that star. And it's still not enough energy for fusion to happen for helium, but it's increasing its temperature quite a bit, right? Heating it up quite a lot, and that heat wants to escape. And so it moves out of the core and moves through the hydrogen that's just surrounding that core. And as it does so, it heats up that hydrogen a lot, right? Enough to the point where that shell actually gets hot enough to start fusing again. So that's when we get to sort of picture B here. We have a helium core that's being crushed down and heated up, and that heat is leaving the core, moving through the hydrogen that's just around the core, and heating that hydrogen up enough to start fusion again. Generally, outside of that is this envelope, which is mostly just hydrogen that's nowhere near hot enough to do fusion. Right? Most of a star is still made up of hydrogen. But yeah, so now you have hydrogen fusing again in this shell outside of the helium core, and that fusion generates a whole bunch of energy on its own and starts heating up the envelope, the hydrogen that's even further out, that makes up the rest of the volume of the star. Heats it up a whole lot, and that increase in temperature increases the pressure of the envelope, which makes it want to expand. So this is the point where the size of the star is going to grow a lot. And as it grows, it starts to get really, really large, get less and less dense, the pressure is dropping on the outside, and the temperature is dropping. So the temperature drops in like the atmosphere of the star. That cooler temperature generally is going to be red. So at this point we have a helium core that's just generating a lot of heat. It's not fusing. That heat is causing hydrogen to fuse in this sort of shell outside the core. That hydrogen is heating up the whole rest of the sun, and so the envelope expands a lot and cools off. So the star ends up being really, really big and red. And being really, really big generally means that you're giving off a lot of light. The sort of surface area or the size of a star goes very well along with its luminosity, how much light it's giving off. So this is the phase that we call red giant. Right? It's gotten very big, turned red. Oh, and it looks like I got ahead of myself again. I think I went through this whole explanation already in the last slide. Let's see if I missed anything. Yep. No, that's pretty much what I just said. Okay. Well, I guess you just watch the video then. There's a nice little animation of roughly what it's going to look like when our sun makes it to this stage in its lifetime, which you don't really need to worry about. That's still about 5 billion years away. So it's going to get bigger and bigger and bigger. Eventually it gets large enough where the atmosphere gets to cool down a bit. It's redder, redder. I'm not sure how far this animation goes, but it's probably the case, yep, that at this point in our sun's life, it will grow so large the Earth's orbit will be inside of the sun. It's not good for the Earth. But again, 5 billion years or so from now. Just to give you a little size comparison, our sun versus a giant star, Delta Udis? Yeah. So even that star is really large, but compared to one of the largest, if not the largest star that we know of at this point, Z Cygni, both of them are small. It's just hard to fathom sometimes, you know. Our sun is already so big, like 110 times the diameter of Earth. And yet, next to some of these other red giants, not very big at all. Here we just compare some numbers for our sun versus a giant star, or red giant. I guess possibly the distinctions of giant and supergiant, we're not going to worry about too much. So this is just another red giant, probably on the larger end of giants, that we're comparing to our sun. So it's in that stage where it finished burning its hydrogen, it has helium, the hydrogen fusion restarts, but only in a shell around the core, and that heat expands the outer layers of the star. And it looks like You're comparing the sun to Betelgeuse, which is in the constellation Orion, I think. Yeah, we'll see that in the next slide. Betelgeuse is about 16 times the mass of our sun. It's quite large. The sun's radius, 700,000 kilometers, but compare that to 500 million kilometers. Almost like 1,000 times larger than our sun. I don't know why we don't have that in AU. I think we've looked at this before, and if Betelgeuse was in our solar system, its size would encompass, it's at least up to Earth's orbit. It might even be like around Jupiter's orbit. Very, very large. But its surface temperature is fairly cool, which is why it's red, 3,600 Kelvin. Core temperature, though, is quite hot, like 10 times what the sun's core temperature is. Luminosity, again, being very, very large, gives off a lot of light, or there's a lot of surface area for light to escape, so there's more light that comes out overall. So compared to luminosity of our sun, 46,000 times that, quite a lot more light. It is far less dense overall, because even though it's 16 times the mass of our sun, it is 1,000 times wider, so much lower density. And the last one, the age, is kind of interesting. So I said our sun is about 4.5 billion years, but Betelgeuse seems to be only about 10 million years. Right? And that goes back to the fact that it being a much larger star, much more massive star, it goes through all these cycles a lot quicker. So even from the process of going from like core to protostar to star, it will have gone through all those stages faster. And then once it makes it to the main sequence, it goes through that phase a lot faster. So after only about 10 million years, Betelgeuse is already a red giant. So the image in the upper left is actually a picture taken by the Hubble Space Telescope of the star, Betelgeuse. And I think it says it's in ultraviolet. And so below the size of the star, we see the size of Earth's orbit, pretty small compared to the size of the star. Even Jupiter's orbit looks like about within the size of the star Betelgeuse. And yeah, I think it is the sort of upper left star in Orion, which we're getting into winter, so should be seeing more of Orion soon. As I mentioned a while ago, we use the HR diagram to think about and like visualize the evolution of like protostar to star, and those look like lines that sort of started up and to the right of the main sequence, and then as the star sort of collapsed and went towards forming an actual star, went towards fusing protons, closer and closer, and eventually land on the main sequence when that proton-proton fusion starts. Now, after it's been on the main sequence long enough, it's going to start to move back off the main sequence. And these are just a number of examples of stars that are going from what our sun's doing towards more of like the red giant phase. So if you look at our sun, or where our sun lies, this is one solar mass, and it looks like it's going to start to sort of move up in the HR diagram, and not really left or right at first. So moving up means it's just going to get brighter, a bit brighter, a bit brighter, and then it starts to get a little bit cooler right around that point where it shows about 10 times 10 to the 9th years. So that's about 10 billion years. Our sun will have moved up and then start to go to the side a little bit. So it gets a little bit cooler, and then it's just going to keep going and getting brighter and brighter and brighter, and a little bit cooler, a little bit cooler, and that's the star just sort of expanding. So by, looks like, about 11.5 billion years, we'll have sort of made it officially to that like red giant phase. So that last portion looks like it takes about another billion years, from about 10 billion to about 11 billion years. It keeps getting brighter and cooler. A lot brighter overall, and a bit cooler. In the end, ends up something like 10 to the 2, 10 squared, 100 to maybe like 1,000 times brighter than the sun is now. So that's a star like our sun, one solar mass. You could look at ones that are a bit smaller, half a solar mass, or a bit larger, 1.5 solar masses, 3 solar masses, 5, all the way up to 15 is the largest one plotted on there. And once again, the timeline, or the times, the ages of the star on the very massive one, are all much less. They're all around 10 to the 7, which is about 10 million years overall. 1.01 times 10 to the 7, about 10 million years, 10.1 million years. And the next dot over there is 11.1 million years. The next dot over is 11.9 million years. And then finally 12 million years. So that whole process goes through a lot quicker than like our sun goes through its process. And also, those really large stars are already so bright that they don't really get all that much brighter in their red giant phase. So it moves off the main sequence, gets a little bit cooler, a bit brighter, and then does this weird swerve thing where it gets hotter and brighter, and then keeps going back to the right where it's getting cooler and like just a little bit brighter. It's almost a horizontal line then. Overall, general trend moving away from the main sequence and becoming red giants is that stars are getting cooler, they're moving to the right, and they're getting brighter, they're moving up on the HR diagram. Right. Well, maybe you're thinking to yourself, these are all very long times, right? Even the short things that I'm telling you about, still 10 million years for a very massive star to go through its red giant phase. Humans aren't around that long. Millions of years on a human time scale is just quite a long time. Right? So, the question is, how do we check our understanding, or like how we think stars evolve? Well, nicely enough, the universe has provided sort of many examples for us to look at. And one way that we test our understanding of the sort of time that it takes a star to go through these cycles, or to go through these different parts of its life cycle, is by looking at groups of stars that all seem to have formed together, so like from the same molecular cloud maybe, the same sort of nebula. So if we look at these groups of stars, these things are called star clusters, then we can make a pretty good assumption that they formed at similar times, and if they formed from the same kind of cloud, then they've also formed from similar elements. Then the main thing that separates each of the stars in a cluster is how massive it is, right? How much dust and gas actually collapsed to form it. If it was a lot, then our theories say that it should be going through its life cycles a lot quicker. If it was not that much, it should be going through its life cycles a lot slower. The idea then is you look at different clusters of stars and you plot them on the HR diagram. Then the most massive ones, depending on how old the cluster is overall, the most massive ones might have already gone to the main sequence and have gone off. Right? So you're going to have dots that are up on the right. The less massive stars in that cluster probably still on the main sequence. So when you plot all these stars in a cluster on an HR diagram, you can kind of make predictions for what those plots are going to look like based on how old the cluster is and the masses of those stars. There are a number of different kinds of clusters that we've seen, or that we do see, when we look out into the universe. We're just going to think about two very broad categories. One is what we call the globular cluster, and the other is what we call an open cluster. The globular clusters are generally very old, and there can be millions of stars in a globular cluster. Right, so the image on the left there is designated M15. Globular cluster is about 12 billion years old and is about 88 light years across. The open clusters, on the other hand, are generally pretty young stars and not a whole lot of them, a few dozen stars. So this image is of NGC 346, and it's estimated to be only about 3 to 5 million years old. It's more than 1,000 times younger than the globular cluster there. Pretty large though, 200 light years across. One thing I'll say is that there's a lot of stuff in the universe, and the way that we keep track of those things is we name them, we categorize them, and unfortunately, a good system for categorizing many, many objects usually turns out to be one that's kind of cryptic. NGC 346. So NGC is sort of like a class or classification type. 346 is like probably the 346th one that we spotted. M 15M is another classification type. I think it's short for Messier. 15 is a 15th one star, probably. That's sort of how our classifications usually work. I say that just because sometimes it's difficult keeping track or differentiating between things that we're talking about. So there might be a number of things that are child NGC, but if it's 346 versus like 105, those are entirely different things. That's just how we do it. So some of these things are well studied enough, or in a sense popular enough, where they might have like a more colloquial name, right? Like the Crab Nebula or the Ant Nebula. But a lot of them, mostly just designations. All right, like I said, that part's a little bit shorter, I think. In the next part, or part 2 of this lecture, I'm going to talk a bit more about these kinds of clusters and look at the HR diagrams and plot measurements from stars and different clusters, and then look at sort of the path that stars take after the red giant phase. So pretty much what I've told you about the evolution of a star, it's like adulthood, then after the main sequence to red giant. Pretty much all stars do that. But once you're past that stage, the next stages in their life cycles can vary a good bit depending on how massive the star is. Some might end up in planetary nebulas. Some might end up just exploding spectacularly in supernova. But that's next time. So, until next time then.